Now we're in section 2.6, where we're going to be talking about limits at infinity. The idea here is that we're looking at the behavior of a function as we let x increase to infinity or off to negative infinity. And a lot of the time we'll have functions which actually approach some sort of value as we let x get arbitrarily big in the positive or negative direction. So for example, here I have y is equal to x squared minus 1 over x squared plus 1. And if you look at the graph, as we move to the right or we move to the left, the curve looks like it approaches the horizontal line y equal to 1, which would suggest that the values of the function are getting closer and closer to 1 as x goes towards infinity or negative infinity. Now over here I have a table of values for this function. I let x be equal to plus or minus 1, plus or minus 10, plus or minus 100, plus or minus 1,000, plus or minus 10,000. This is an even function, so plugging in a positive or negative value for x gives the same result. The resulting values for the function are 0, 0.981, 0.9801 repeating, 0.999, 8,00001 repeating, 0.59, 8, etc. repeating. And by the time we get to 10,000, the values are 0.9999999, blah, 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 blah. So clearly these values look like they're getting closer and closer to 1. This suggests that as x goes towards infinity, or negative infinity, the values of this function approach 1. So here's the definition. L is the limit of f of x as x approaches infinity if we can make f of x as close to L as we like by taking x large enough. The bigger we take x, the closer and closer we can make it get to L. Similarly, if we take the limit of f of x as x approaches negative infinity, we can make the values of f of x as close to L as we like as possible, but we take x big enough in the negative direction. Again, when I say big in the negative direction, I mean a really big negative number, really big in magnitude. The notation we use is very similar to that we use for regular limits. We write the limit as x approaches infinity of f of x by writing the usual limit notation, but we write x with an arrow approaching infinity. And for negative infinity, we write negative infinity. Remember that when we have an infinite limit, that is, when the y values approach infinity as x approaches a number, we end up with a vertical asymptote. Similarly, when we have a limit at infinity, if the limit of f of x is L as x approaches plus or minus infinity, we end up with a horizontal asymptote at the line y is equal to L. So we get L from the limit, and it's a horizontal line, y is equal to whatever. Now let's note that the graph of y is equal to f of x gets closer and closer to the line y equal to L, and it may even intersect it once or infinitely many times as x goes to plus or minus infinity. This is in contrast to a vertical asymptote where the graph never hits the vertical asymptote. So here are three different possibilities. This is the graph of 1 over x. As x goes to infinity, the graph approaches the horizontal asymptote y is equal to 0. Doesn't hit it ever. Over here, x over x squared plus 1, we again have a horizontal asymptote at y equal to 0, and the graph actually goes through the y value of 0 at 0. So it hits it once and then gets closer and closer without ever hitting it again. I can also have sort of oscillatory behavior. If I take the function sine of pi x over x, then this is going to be something that also has a horizontal asymptote at y equal to 0. However, it oscillates infinitely often above and below the asymptote. The important thing is that the values are getting closer and closer and closer to 0. Some, in an absolute sense. Sometimes they're equal to 0, but they're always getting closer and closer as x gets bigger and bigger. So here are two common examples of limits at infinity that I would like us to know. First of all, arctangent has limit pi over 2 at infinity, and at negative infinity it goes to negative pi over 2. Graphically, it looks like this. We have a horizontal asymptote at pi over 2 as x goes to the right. We have a horizontal asymptote at negative pi over 2 as x goes to the left. Note, a graph can have one horizontal asymptote, it could have two, it could have none, but it can't have more than 2. Okay. Our second common example is the limit as x goes to negative infinity of e to the x. That limit is 0. That corresponds to the fact that as we approach negative infinity, as we go off to the left, the tail of the exponential function gets closer and closer to the x-axis, the line y is equal to 0. Okay, so here I've given the graph of a function, y is equal to f of x, and let's find the vertical and horizontal asymptotes for f of x, and also let's find the corresponding infinite limits or limits at infinity corresponding to each of the asymptotes. So I've colored in red 2 vertical lines and 2 horizontal lines. Let's look at the vertical lines first. First, I have a vertical line at -1, so that is one vertical asymptote, x is -1. I also have one at 2, so that's another vertical asymptote, x is equal to 2. Let's look at what's happening at -1. As we approach -1 from the left, the graph is going down off the bottom of the chart, so that means that the limit as I approach -1 from the left is negative infinity. As I approach -1 from the right, the graph is going up off the charts, so that means that the limit as I approach -1 from the right of f of x is positive infinity. At 2, whether I approach from the left or from the right, I'm going down, so that means that the limit as x approaches 2 of f of x is negative infinity. Okay, note that the coordinate for the vertical asymptote corresponds to the x value that we're approaching in the limit. It's not the value of the limit. The vertical asymptote's coordinate corresponds to the x value we're approaching. Okay, so for the horizontal asymptotes, we have 2 horizontal lines here. There's one going through y equal to 3, and one going through y is equal to -2. So those are our 2 horizontal asymptotes. The first one, y is equal to 3, well, how does the graph approach it? We see that as we move to the left, the graph is getting closer to y is equal to 3. So that's x going to negative infinity. So the limit as x approaches negative infinity of f of x is 3. And then we see that the graph approaches the line y is -2 as we go to the right. It hits it once and then it gets closer and closer to it. So the other asymptote, the other limit at infinity is the limit as x approaches infinity of f of x is -2. Notice that the coordinate for the horizontal asymptotes corresponds to the value of the limit. So vertical asymptotes correspond to the x value we're approaching. The horizontal asymptotes correspond to the actual value of the limit. Question 1. Sketch the graph of a function with, first, 2 horizontal asymptotes, one at y equal to 0 and one at y equal to 2. Second, draw one which has exactly one horizontal asymptote at y equal to -1.